My name is George Arslan, and I'll be talking about my review of plant viral nanoparticles for diagnostics and therapeutics. So, nanoparticles have the ability to carry large drug payloads while also providing an accessible site for ligand attachment to allow for specificity. By altering the chemical and physical properties of these materials, such as shape or elasticity, their in vivo properties can be drastically altered. The problem, however, arises in that the vast majority of these technologies under development only offer low aspect ratio materials, that is, an aspect ratio under 5. Aspect ratio for nanoparticles is generally defined as their length times their width. Even those that do have high aspect ratios, such as carbon-based nanotubes and phylomyl cells, are hindered by their lack in biocompatibility and size. This lack in high aspect ratio materials is mainly due to the challenges that come with trying to design nanoscale materials in 2 dimensions using synthetic materials, such as addressing polydisparity and poorly controlled chemistry. So a solution is needed to address this low aspect ratio or the low aspect ratio, or the materials that have high aspect ratio but low biocompatibility materials. So the solution offered from this paper are plant viral nanoparticles. Viral nanoparticles are virus-based nanoparticle formulations to be used as a building block for designing novel materials with diverse properties. They can be plant, bacteriophage, or animal viruses, along with being non-infectious or infectious. These types of nanoparticles are especially advantageous due to their natural occurrence, meaning that they are more easily biocompatible and degradable. This, combined with their capabilities of being easily engineered, make them an extremely attractive nanomaterial for biomedical applications. These plant viral nanoparticles seem to offer a solution to the low aspect and biocompatibility issues that come with other nanoparticles. They have already been established to have the ability to develop gene therapy vectors, vaccines, and oncolytic viral therapies. Plant-based viral nanoparticles in particular are attractive because they have been shown to be non-pathogenic in mammals. Additional advantages include a diversity in size and shape, being truly monodisperse, meaning that they are of uniform size, highly symmetrical, and having a structure known down to atomic precision. All of these allow for an appealing target to engineer nanoparticles with features for targeting ligands, drugs, or imaging molecules. So specifically, this paper is looking at using the filamentous plant viral nanoparticle potato virus X, or PVX. This is an emerging filamentous VNP platform that they've developed in their lab. It allows for easy engineering through genetic modification or bioconjugate chemistry. To test its efficacy, they are comparing it to a spherical VNP called cowpea mosaic virus, or CPMV for short, which is a plant virus with a low aspect ratio. It is a good nanoparticle for comparison as it has been extensively studied and characterized, including its biodistribution and tumor targeting, both of which will be featured here. The PVX structure consists of nanofilaments at 515 by 13 nanometers, giving it an aspect ratio of 40, along with 1,270 identical protein units. This is the monodisparity that we discussed earlier, and each of these protein units can be chemically addressed via their reactive lysine side chains using NHS chemistry. The CPMV structure, on the other hand, consists of only 60 copies of a small and large protein, along with offering 300 reacting lysine side chains per particle. So to get into the experiments and results, we'll talk about they first started off their experiments by looking at attaching polyethylene glycol, or PEG, and a near-infrared dye, Alexafluor 647, or just A647, to both PVX and CPMV. PEG is a vital component in developing VNPs because it significantly reduces the immunogenicity of VNPs while also reducing undesirable nonspecific cell interactions, prolonging plasma circulation, and increasing stability. A647 is a commonly used dye for molecular imaging and has high compatibility with the VNP carrier system, along with being used in fluorescent imaging modalities. To characterize the attachment of the PEG in A647 to the lyse residues of the VNPs using NHS, a combination of UV and visible spectroscopy, TEM, denaturing gel electrophoresis, and zeta potential measurements were done, with the results being shown in the first figure here on the left. They showed that the PEG 5000 and A647 were both covalently attached, with CPMV having 53 A647 dyes and 35 PEG 5000 chains, while on the other hand PVX boasted 386 dyes and 380 PEG 5000 chains, clearly outshining the CPMV in attachments. Next, tumor homing and tissue penetration properties were evaluated and compared through the use of human fibrosarcoma and squamous carcinoma tumor models. By dyeing the two VNPs with different fluorophores, it allowed for easy side-by-side comparison. After intravenous administration of both VNPs, it was seen that both accumulated in solid tumors, with the key difference being that the PVX accumulated at the center of the tumor, while CPMV nanoparticles tended to be distributed throughout the tissue with no localization to the tumor center. This deeper penetration is hypothesized to be due to the filamentous structure of the PVX nanoparticles, along with the net positive surface charge of the VNP, which has been shown to lead to further diffusion through collagen, since negatively charged particles may aggregate in the positive collagen extracellular matrix. To continue, they talk about tumor homing and penetration. So tumor homing was quantified using an animal model of colon cancer. After sufficient tumor growth, the VNPs were administered, and results indicated that PVX again showed enhanced tumor homing when compared to CPMV, along with providing distinct biodistribution profiles as seen in these figures. Imaging and quantitative biodistribution indicate that the CPMV VNPs tend to localize to the liver with negligible tumor accumulation, whereas PVX shows enhanced tumor homing. This enhanced homing could be due to the filamentous structure of the PVX versus the spherical structure of CPMV, as nanofilaments are thought to penetrate tumors and tissue better, thus increasing tumor retention of the PVX. These nanofilaments also tend to evade phagocytosis better, meaning that they can stay in circulation longer and can therefore have a higher chance of accumulating in the tumor. However, in their data, they show that CPMV actually has a higher circulation time, so this could be something that they look at in the future. Biodistribution was analyzed using fluorescently labeled and pegylated VNPs, and after fluorescence intensity and normalization was done, it was seen that CPMV accumulated 71% in the liver, 13% in the spleen, and only 9% of the particles ended up in the local to the tumor. On the other hand, PVX had 55% in the liver, 23% in the spleen, and 15% local to the tumor, clearly having higher increase. So overall, it seems as though the rod-like structure and high aspect ratio of the PVX has given it advantages to tumor localization over its spherical lower AR counterpart. To wrap up, overall, I believe that the filamentous high aspect ratio VNP pathovirus X had the ability to penetrate farther into tissue and localize the tumor significantly better than spherical lower aspect ratio nanoparticles such as CPMV. As an initial study to quantify the abilities of PVX and versus prototypical plant VNPs such as CPMV, this paper has done good work to show the advantages that come with choosing it. There is some work to be done to further increase the stability of PVX, but as a starting point, it seems as though it could be a much better choice to use in the future. There's plenty of engineering and development that can be done in these structures, so there's plenty of room to improve this vehicle. Thanks for listening.